Record. That's the fun part about being the teacher. It's so much more entertaining because you can just move around and do whatever you want. Well, I guess not whatever you want. Although that would be fun. All right. So today we're going to finish chapter 4. And the reason I'm in such a rush to do it is because we've tested what we need. We're going to start talking about the normal approximation to the binomial. So now we link the normal distribution with the binomial. Okay. And so that part is going to be really important. That's going to show up on our final exam. Okay. So we didn't have time to do it for this quiz because we kind of did a switcheroo, but that's okay. So it will be on quiz 3, okay, and the final exam. So first part is important. And then I'm going to rattle off some other distributions that I told Claude I would say. And then he can teach you more about them. Okay. So first off, where are they? Going to do a little, right a little bit, bump it to the top. All right. So main part that we're going to talk about today is the normal approximation of the binomial distribution. Yeah. So imagine, right? Let's say, what was the binomial example we had last day? I can't remember. Oh, whoops. What was it? Oh, okay. Yeah. So if you have 10, 18 to 20-year-olds or whatever the age range was, right? And you want to know, okay, what's the probability that 4 of them have consumed alcohol, right? You can use the binomial distribution, right? Because it satisfies the criteria. Right, and so first, I guess as a little bit of review, tiny bit of review. Okay, a binomial is when we have independent outcomes and only 2 possible outcomes, right? Not necessarily just only 2, right? But you can boil it down to 2. So a lot of situations you can turn into binomial situations, okay? But only 2 possible outcomes. And we said, okay, the probability that x equals k, which is really just shorthand for the probability of k successes, okay, we find by using the choose function n choose k. So n is the number of trials, k is the number of successes. How many ways can I rearrange k successes in n trials? And then p to the power of k, where p is the probability of a success to the power of however many successes you need to have, and then q to the n minus k, where remember q is 1 minus p, right? Or you can just write 1 minus p if you prefer, but I think the q is cleaner. And then to the power of however many failures you have. So that's what we arrived at last day, right? We spent some time kind of developing this formula, so it wouldn't be so scary, although maybe it still is. That's okay. Just need to know how to use it. Okay. And we found things like, okay, the probability. So for example, the probability that x is less than or equal to 2. What did we have to do? We had to find the probability that x equals 0 plus the probability that x equals 1 plus the probability that x is equal to 2, right? So we had to do this calculation 3 times and add them up. Okay. So now consider you're looking at 100 people. Okay. So now consider 100 youths. Make myself sound old. Youths. But I'm old and lazy, I guess. 18 to 20-year-olds, blah, 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 right? So now consider 100 youths. What's the probability that less than 40 have drank? Uh-oh. What is the probability less than 40 have drank alcohol, I guess? Uh-oh. Same scenario, right? We know how to do it, but hopefully you don't want to do it, right? Because what are you looking at? You would have to take the totally, right? You'd have to take the probability that x equals 0 plus the probability that x equals 1 all the way up to 40. Hopefully no one wants to do that. No, right? Okay. Normal approximation to the binomial, to the rescue. Okay, so here, luckily, we don't need to use this as long as some conditions are satisfied. Okay. I really shouldn't have brought this in yet. Let me just cut that out. I keep bumping it. So luckily we don't need to use this as long as the binomial conditions are satisfied, which they would be, of course, otherwise you wouldn't be trying to do these calculations, right? So as long as the binomial conditions are satisfied and n times p, okay, n is the number of trials and p is the probability of success. Okay, so in 100 trials, if the probability of success is 0.6, right, then n times p would be 60, right? And so what, in words, what is that? That's the expected number of successes, right? N times p is the expected number of successes, right? And just to kind of re-emphasize, n is the number of trials and p is the probability of success. Oops. Okay. So the expected number of successes has to be greater than or equal to 10. You have to have a large enough sample. I'm talking to your Siri. She's like, hey. And another thing, so we have to have a sample size or a number of trials large enough to be able to detect 10 successes. Okay, and the reason we have, so the n has to be large enough, but also p has to be large enough. If you have a very, very small p, right? So if the probability of success is very, very small, meaning you have a rare thing happening, which is common, right? Common to have a rare success, right? But if you think about diseases and things like that, right? Bankruptcies, whatever, right? The successes, the things that we're interested in are relatively rare, right? And so then your P is very, very small. So you need to have a number of trials to kind of bump that up so that the total number of expected successes has to be 10. On the flip side, right, if a failure is very rare, then we have to make sure that N times Q, which is the expected number of failures, also has to be more than 10. Okay. So N times Q, which is the expected number of failures, also has to be greater than or equal to 10. Okay. These conditions will always be satisfied for us, right? And in general, right, if you're applying this in the real world, they will be satisfied, but you do have to show that you checked them, right? So it's one of those things, okay, now I have to check that this is true. Okay, it is, great, moving on, right? But you still have to do it, okay? And so on top of the binomial conditions, right, if you want to use the normal approximation to the binomial, which we haven't introduced yet, but I think you kind of have a clue that, okay, I'm going to be able to use the normal distribution to calculate binomial probabilities, which is like crazy, but it's true, guys, it's true. So now I'm going to paste that. And at some point here, I ended the review, and maybe I'll sneak that in there. At some point, it became new stuff, and it was very early on. Okay. Maybe after this, doesn't matter, whatever. Whatever, okay. So a lot of words. Let's go ahead and read them. All right. The binomial distribution with probability of success P, okay, and that's true for what we were talking about before, is nearly normal. Okay, so that's a good sign, right? Because we know how to deal with something that's nearly normal, right? I can calculate Z scores. I can use the table or software to find probabilities, right? So that's a good thing. Okay, when the sample size N is sufficiently large that N times P, so that's the number of successes, and N times 1 minus P, which is the number of failures, expected number of failures, are both at least 10, right? So that's what we outlined already. There's actually no news here. We've already talked about this, right? The approximate normal distribution has parameters. Let's remind ourselves what parameters are. Parameters are measurements from the population, right? P and P. Okay. So it has parameters corresponding to the mean and standard deviation of the binomial distribution. Okay. So what we're going to find is that, okay, the mean of the binomial is N times P. It's the expected number of successes. Okay. A little bit sneakier is the standard deviation. The standard deviation is going to be the square root of NPQ. Okay. And so that's just, it's on your formula sheet, right? And so if you find that, okay, right, you stumble upon something like this, where you're thinking, I don't really feel like doing all these calculations, that's crazy, right? Then you can check to make sure that you have at least 10 successes and at least 10 failures, which means what? The absolute minimum sample size that you can have is 20, right? So absolute minimum. Let's take it a step further. What would P have to be? 0.5, right? Q would have to be 0.5 in order to be able to get away with a sample size of 20. Right? Okay, so the mean of the binomial is n times p, and the standard deviation is the square root of npq. Okay? And so now we can use these values, all right? We can say, okay, if it's approximately normal, then it's centered on the mean, which is n times p, and the standard deviation is npq. I use npq. Okay, so now what we can do is, if, for example, we want to try to solve this problem that we started with, right? We now consider 100 youths. What's the probability less than 40 have drank alcohol, right? And so we're going to have some expected value, so some mean, which is the center, and then we're going to be able to find some spread. Let's see here. What is that going to look like? I can't remember what the mean was. Yeah, right. It was something like, oh, yeah, 69.7. Okay. So from last day, right, P was 0.697. And the probability of success was 0.697. And now we're gonna answer this problem, okay? So now you have 100 youths. What's the probability less than 40 have drank alcohol? Okay. So now N is gonna be, and maybe I'll just clarify here, we can use this to find the probability that X is less than or equal to 40. Okay. So we're gonna let N be 100. P is 0.697, which means Q was 0.303, I think I remember. Yeah, right. And it looks reasonable, but if I'm wrong, correct me now. Stop me now. Huh? Okay, nice. Okay, so now what we're gonna have is, okay, I want to use the normal approximation to the binomial, which means I need to check 2 additional conditions, right? I've already confirmed that this is a binomial, right? And so it's binomial, check. Okay. Next thing I want to check is that N times P, which is in this case 100 times 0.697. And these I do get kind of sloppy and I go equals across, which I usually hate, but I'm just checking conditions, right? So 69.7. You don't do any rounding here because this is an expected value. And so there can be a partial person in there, right? Because it's just what you would expect, which is greater than or equal to 10. I like to highlight that I'm checking a condition. Okay, so that's satisfied. Next thing I need to check is that 100 times the probability of failure, right? So the expected number of failures, 0.303 is 30.3, which is also greater than or equal to 10. Can I make my check mark look as good? No, I cannot. Is it just me or is this a really nice check mark? It's really nice, right? Thank you. Thank you. They come around every now and then. All right, most of the time, they're not that nice. Okay, so great. Now we can use the normal approximation to the binomial. So I'll just say the conditions are satisfied. So we may use the normal approximation to the binomial. If you have software, you don't have to use the normal approximation to the binomial, but I'm pretty sure that it uses the normal approximation to the binomial if you reach a large enough n. And so I think even in programming, right, at some point it switches to the normal approximation, but I'm not 100% sure on that, but the answers will be pretty much the same. All right, so what does that mean? How can we use this normal approximation to the binomial? Well, if we go ahead and draw our normal curve, not so lifted off here, there. We just decided that the mean 69.7, right? So mu, you've actually already calculated there. So mu is n times p, which is 69.7. Oh, maybe not green. Sigma is the square root of npq, which is the square root of 100 times 0.697 times 0.303. And don't forget that square root. 100 times 0.697 times 0.303. I'm going to just write it out, 21.1191. And I'm keeping that square root for just one step longer, because then hopefully when you look back and you're saying, I did exactly what, oh no, I forgot the square root. So then I'm going to take the square root and I get 4.59555198. Okay. All right. So I'm going to round this because I don't want to use all those. Let's use 4.60. Strong rounding, but that's okay. All right. In general, you want to match the number of decimal places at least, right? So the mean has 1, so you need at least 1 for sigma. That's just a general rule of thumb. Okay. But sometimes sigma, you want to have a couple more. Okay. The mean is 69.7. We want to know what's the probability that less than 40 of the 100 people have drank alcohol. Now, 40 is going to be on this number line, right? Starting here, probably at 0, right? In this case, you can't have a negative number of youths, right? Youths can be negative, but you can't have negative youths. Okay, so starting at 0, presumably, going all the way to 100. Okay. So then on this number line, right, I'm expecting 69.7, but there's some wiggle room around 69.7. And now we want to know what's the probability that less than 40 have drank, which means that this is going to be the value that I'm interested in. That's the value I want to find some probability associated with. All right. Next stop, z-score, right? So z, right, as soon as I have a normal distribution, I can use a Z score to find probabilities. And so now Z is X minus mu over sigma. What am I finding? I'm finding how many standard deviations is 40 from 69.7. Okay. So I have 40 minus 69.7 divided by 4.60. All right, 40 minus 69.7 divided by 4.6. Wowzas. Negative 6.4565211739. Oh boy, what do we do? That's so small, right? Why do I say that? In the 68, 95, 99.7 rule, right? I only had to move out 3 standard deviations to cover 99.7% of the middle data, right? Or curve. So now being almost 6.5 standard deviations away, well, that's like way out here, right? So the probability in the tail now, approximately 0, right? It's not going to be 0. It's approximately 0, right? You could have 35 students who haven't drank. You could have 30 students who haven't drank, right? But the probability is very, very, very small. Okay. So the probability, you know what? I want to show you on the table how that's going to behave. And I'm going to crop top it to what I want, just what I'm interested in here. It's going to be there. Okay. And I'm just going to focus on the one-sided P because two-sided, you can just figure out. You don't actually need the two-sided. Although it's going to be nice later, you'll find, okay, to have it. Okay, so what's happening here? Let's start on this side, because I know you guys had to deal with, okay, I understand that the Z curve or the Zs are symmetric, right? So whatever happens on the upper side, so the positive side is going to happen on the lower side, but in the other direction, right? So we're all good with that. But then what happens here? There's actually a Z of 0 here, right? Starting at 0, and then we start moving out to 0.674, 0.841, blah, 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 right? What's the probability in the tail from 0? 0.5, right? So here, if you want to have kind of a complete table, right? You would add the 0 and the 0.5. Okay. Now I'm moving out, blah, 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 all my Zs. At a Z of 3.291, I have an area in the tail of 0.0005. Very, very small, right? What's my next stop? Even more, infinity, right? Once I pass 3.29, we stop caring. We say, well, that's a small probability. And then we're done, right? Doesn't matter how small at that point, you'd use software for that. But at infinity, then the area beyond infinity, and I know you're thinking that can't happen, so the probability is 0, right? But not until you reach infinity. Okay. So it might be helpful to kind of put those two endpoints on the table, or at least mentally, right? Because now what happens? Well, our Z that we calculated would fall somewhere between 3.29 and infinity, right? Doesn't matter. It's somewhere in there, right? And really what we're doing is the absolute value of this, right? Dropping the negative. And so these guys are the ones that I'm interested in. So how do I write that? I say, okay, since, and I'm always going to use this layout, okay? I start in the center of my page and I write out the absolute value of Z equal to negative 6.4565. Let's stop there. And the reason I use this layout is because I hate thinking about inequalities. They take a long time for me to think about, okay, the alligator eats the big one, but am I the alligator or is this the alligator? Anyways, so I have a hard time with that. But a student actually told me, well, if you just want to read it as less than, you have to just make an L with your fist, right? And then you can just read it as less than, right? If it makes an L, you read it as less than. So 3.291 is less than 6.4565, which is, and this is a fact, less than infinity, right? Okay. Now I translate that into probabilities. So since this is true, the probability, and maybe I'll say the tail probability. Notice that I'm using the same inequalities here, right? And so that's why I like this setup, but the problem is it gets confusing, right? Because I need to start with a smaller probability on the left-hand side and then bigger on the right-hand side, which means I need to read it from right to left, right? So it's greater than 0, but less than 0.0005. Now I can use that and say, therefore, the probability less than 40 youths have drank alcohol is between 0 and 0.0005. I don't have my RStudio booted up and it's going to take forever, so I'm not going to do that. But you can use the P norm, or there's P binom, where you can use a binomial, right? And I think it's, is it D binom? Q binom. Doesn't that work backwards to find the, anyways, I can't remember off the top of my head. That's the thing about coding. I know it exists, so I don't need to remember it. You can just find it. Yeah. That's okay. That's okay. I feel like you guys had to do that quiz to be ready to receive this, right? So we're using it, but now we're going to keep using this format, right? So as long as you're constantly becoming more comfortable with it, that's a good thing. Okay. All right. So, okie dokie. I have an example.
So this curve can be used for both z-score and that mean, right?
Yeah, and the binomial. Is that what you mean? Yeah.
So like to interpret this into like the curve where that data set falls between, like, let's say 95% of data, where does that 95% of data fall into this curve?
Mm-hmm.
There is one curve for z-score and there's another curve for our data. That's for the middle line is z equals to 0, right?
Yeah.
But here in the middle line is mean.
Yes, but okay. Okay, so that's good. So this number line is for our data. Okay. When we calculate Z, basically what we do is we take this curve, copy, and I'll just keep it there and then paste another copy right underneath it. Maybe not right on there. Okay. So I'm gonna erase. Okay. So here, and then sigma for this top one was 4.60. Let's say I'll do approximately. Okay. Now, yeah, exactly. This is a Z. So the mean is 0. Sigma is, and I'll use the same color code. Sigma is 1, and Z is negative 6.46. Right, but all we've done is we've taken this thing and we've shrunk it down. We just kind of took it and put it on a standard scale, right? But the area under the curve is still 1. The area that we're interested in, right, proportionately is going to be the same. Okay? And so that's why you need to use this this gateway drug of Z. Right? And so it's always going to go from an X to a Z to a probability. Or you can move the other direction, right? I give you a probability, right? What number of students, right, are in the 10th percentile or something like that, but you need to find Z before you can find X, right? So it's a gateway in both cases. Yeah. But yeah, so I draw this curve, but whenever I've typed up solutions, I only draw the Z curve because I don't want to reprogram it every time when it looks the same, right? And so I cheat and I use the Z, but the idea is the same. Okay, nice.
Because when we compare both of the graphs at the same time, the answers kind of make sense because, like,
yeah,
there's no way that more than 40% of those data will be in that data set. They fall far away from the mean. That's why. Like,
yeah.
From this example, I hope we can clearly see that they don't fall under that curve.
Yeah. It's not clear because 4.6 is hard to think about, right? You would have to take away 4.6 3 times only to realize that, okay, well, 40 is still quite a ways away. So that's why we standardize. That's why we calculate the Z, because it does that thinking for you. Right. Okay. All right. Question is, yeah, we should do this example. I know I'm going to run out of time, so I'll just mention it here. Just like I said to Claude, tomorrow I will say the words geometric distribution, negative binomial, and the Poisson. And he's going to be like, you heard about this in Stat 230. And you guys can say, yeah, for like 10 minutes. And then he'll be like, Emily, what are you doing? It's not important for us. It's important later, but for our core skills, we don't need to know it. Okay, there's a geometric distribution. Okay, and okay, the geometric does what? If the probability of a success in one trial is P, so that's the same as the binomial, then the probability of failure is 1 minus P, same as the binomial. Then the probability of finding the first success in the nth trial. Okay, so it's another distribution that you can use to find the probability of finding the first success in the nth trial. Okay. Flipping a coin, for example, you want to know what's the probability that the first time you see a tail is on your 6th flip. Okay. So then n is the 6. Okay. So then you had to have seen 5 failures first, right? So you force 5 failures followed by a success. Okay? So here it's the probability of finding the first success in the nth trial. Okay. And what I'll do is I'll post the solutions to these so that you have them. And then don't worry, I posted about an assignment, but I'm going to break off the geometric, the negative binomial and the Poisson questions for a bonus assignment. If you want to boost your grade, or if you want to forget about it, that's fine too.
So everything that's under n trial are failures.
That's under what?
Under n trial.
Mm.
That's the first success in n trial. That means the rest of them are failures.
That's right. Yeah. So then you can find that probability using the geometric distribution. Negative binomial is the probability of observing the kth success on the nth trial. Okay. It's really just a special case of the geometric, right? And so here I'll highlight that it's the probability of the kth success on the nth trial, the 4th success on my 10th flip, right? So you can find that probability. And
That can be 0.
yes, it can be close to 0. Yeah. Now the Poisson is for counting, okay? And so the Poisson, where does it say? The number of observed, no, that's not what I wanted. Where does it say? We're K, ba, 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 ba. Okay, I guess I do this. If events happen at some rate lambda, this is lambda. Then the probability that you observe K events in some number of minutes or hours or in some interval, it can be either in time or space. So usually if you're talking about the number of defects in a piece of lumber or something like that, right, then they happen with some rate, and you can find the probability that you have at least that you have 4 defects, right? Maybe that's your cutoff point, right? Then you can't use that piece of lumber, for example. Okay, and so then you use that lambda, right? So the probability that you observe K events at some rate, then you take the rate to the power of K and e to the negative lambda, right, over K factorial. Kind of skipped K factorial, but K factorial is K times K minus 1 times K minus 2, all the way up to 2 times 1. You just multiply through. Okay. And like I said, I'll post the solutions to these questions, but let's just, time flies when you're having fun. All right. Let's just talk about this one with my last couple of minutes here. Suppose that Canadian Blood Services anticipates the need for at least 1,850 units of O negative blood for a particular region this year. It estimates that it will collect blood from 32,000 donors, and only about 6% of people have O negative blood. What is a success in this case? In this case, a success would be having a donor with O negative blood, right? So donor, or I'll say O negative donor. What are N and P in this case? N is the number of times that I try to get an O negative donor, right? 32,000. P is the probability of it being an O negative donor, 6% or 0.06. Let's see here. What is the mean and standard deviation of this distribution? Well, we know the mean is N times P, so the mean is 32,000 times 0.06. I get a mean of 1,920, which is also how many O negative donors I would expect to see if I was able to get 32,000 donors, right? That's my expected value, but we also know that there's variability around that. Sigma is NPQ. 32,000 times 0.06 times 0.94, I think. Phew. So times 0.94 and then square root that. I get a sigma of 42.48293775. Okay. Hate it when it does that. I know I'm out of time, so let's just read through them quickly. Set up the formula for getting exactly 1,850 units of O negative blood from 32,000 donors. Why do I only want the formula? Because that choose function, your calculator will not be able to do it. Try 32,000, choose 1,850. Math error, it says on mine. All right, it just says, sorry, I can't do that. What are we asking it to do? Make a tree with 32,000 layers and then figure out how many times I can get exactly 1,850 units. No, even our calculator is like, no, I won't. So that's why it says set up the formula. Okay. Check the assumptions for the normal approximation to the binomial, right? Check that it's a binomial, which we assume it is. And also N times P has to be greater than 10 and N times Q has to be greater than 10. And then I'll let you work on that one because I know I'm over time, but I just wanted to keep you a little bit longer because I don't get you all next week. All right. If you have any questions, let me know, but I'll post these solutions.
Is it all right? Is it all right?
And, oh, hello.
Thank you.
Well, maybe not.
Thank you.
Thank you. Have a great reading break. See you on the other side. May you finish all the things that you want to finish.